Okay, so we continue the lesson of complex numbers. We want to talk about the polar form of a complex number. So let me review a little bit of what we learned so far. So we learned that a complex number, the standard form of a complex number z, is a number of this form, yes? My recording, yes. So, and then we know that I is the square root of -1, or in other words, I squared is -1. And we also learned about the complex plane, if you remember. The complex plane is essentially the same as the coordinate system, but the horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. And then I can represent every complex number by a point on the complex plane. But for example, if this is A and this is B, then this point represents the complex number Z that you see there. And we also learned that another representation is a vector representation, so that when we realize where the point is, we connect the origin to that point and put an arrow here. This is also representing the same complex number, and this length, which is the distance from the complex number to the origin, is called the absolute value of the complex number. So the absolute value of the complex number is the length of this orange arrow or vector. This is the distance from the point on the complex plane to the origin. And if you remember, the formula is square root of a squared plus b squared, the real part squared plus the imaginary part squared. And then we also learned about something about this angle. This angle, if you remember, is called the argument of the complex number. So theta is the argument, which is denoted by arg of z. And that is the angle that this vector makes with the positive part of the real axis. So for example, if this vector is here, then you shouldn't take this angle, you should take this bigger angle. Yes, this is the angle. And then I told you that there are some conventions for theta. The convention that is usually easier to use is the convention that theta goes from 0 degrees up to not including 360 degrees. Or in the radian mode, you can write 0 radians up to 2 pi. Yes, okay. And now, for example, let me just give you an example to refresh your memory. Say that we have z equals to, I write the numbers that I can use my memory to solve them without calculator. So let me write this. So this is a complex number. Of course, sometimes we can also put I on the left side, I times that, and this times I, doesn't matter. So if I ask you what is the absolute value of this complex number, then according to this formula, it becomes square root of, the real part is 3 squared. The imaginary part is the part without this I, which is minus square root of 3 to the power of 2. And you calculate this. So this becomes 9, square root of 9, and then plus 3, which is the square root of 12. That's correct, but if you want, you can write it if you want to simplify it a little bit. And the square root of 4 is 2. It's 2 square root of 3. Of course, if you stop here, that's also okay. So for example, if I give you this complex number and I ask you what is the absolute value of this complex number, the answer is a real positive number, and that is 2 square root of 3. But I can also ask you about the argument of this complex number. So I can ask, what is the argument of the complex number z, yes? So in that case, I need to somehow locate the point so that I can sketch a graph to understand how to find this angle. Yes. So what do? You try to locate that point. The real part is positive 3, but the imaginary part is minus a square root of 3. So, for example, let us say this is 0.3, and let us say this is minus the square. You don't need to be precise at all. You just want to locate approximately where the point is. So this is my point. Yes? This point is this point. And then you need to connect the origin to this point and put the arrow on the side of the complex number. But then you realize this angle from here to here is the argument. Yes? But then I need to find that. If you remember, I told you that it is better to think about these acute angles. When you found them, you can adjust this one. For example, let us concentrate on this one. Let me call it alpha. And you always use tangent. Okay, so tangent of alpha is the length of the opposite side. But the length of the opposite side is the square root of 3. I'm talking about the length. So the length cannot be negative. So the length is the square root of 3 divided by the length of the adjacent side to alpha, which is 3. Yes? Okay, if this number is not a famous number, you have to use your calculator, but here I have it in my memory, so alpha is tangent inverse of that number. And this turns out to be 30 degrees, or if you want to write it in radians, it is pi over 6 radians. But be careful, alpha is not the argument itself, the argument is this angle. Of course, it is clear that the whole angle is 360 degrees or 2 pi. I already know alpha, so if I subtract it from 2 pi, I get the theta. So theta that I am looking for is 2 pi, which is the whole angle, minus this angle pi over 6 that I found here. And if you do the common denominator, it is 12 pi over 6 minus pi over 6. And this becomes 11 pi over 6. Okay? So the argument of z is simply 11 pi over 6. So this is what we had before. And I told you that you might wonder why we are doing this, why this is important. And this is the topic of today's lesson I want to discuss about. That's the polar form. Okay, so let me just teach the new lesson. So let us say that I have the complex plane and I know that this is the vector for my z. And let us assume that the real part is A, and let us assume that the imaginary part is B, and let me also assume that the argument, I call it theta. Yes? So if I ask you to write this complex number in a standard form, you write z is equal to a plus bi. This is something you already know. But now we want to learn how to write this complex number into polar form. Okay? First let me tell you what is the meaning of the polar form. You might be a little bit astonished why we are making life harder for ourselves. But then the reason will come clear shortly. Okay, so instead of A, let me consider this triangle. And I ask you to write for me cosine theta. So cosine theta is the adjacent side, which is A, divided by the hypotenuse. But what is the hypotenuse is the length of this vector, which I told you is absolute value of the complex number. So this length is absolute value of the complex number. So I divide it by the absolute value of the complex number. And if I ask you what is sine theta, you will tell me sine theta is the opposite side, which is B, divided by the hypotenuse, which is the same thing. But from here, if I multiply everything by absolute value of z, A becomes absolute value of z cosine theta. And from here, B becomes absolute value of z sine theta. And then I put these back into the original form of my complex number. So then it means that the complex number z is equal to, instead of a, I put absolute value of z cosine theta plus, instead of b, I put absolute value of z sine theta, and of course I have an extra I here. Yes? And then you see that for simplicity I can factor this number out. So this means that the absolute value of z, I pull it out, and what is left for me, cosine theta is left from the first one. From here, I and sine theta are left for not getting confused, so let me write I on the left side rather than the right side. This is called the polar form. So this is called the polar form of the complex number z. Okay, and usually in the complex numbers, this number is denoted by r. So the absolute value is usually denoted by r. So if I give you a complex number and I ask you to write it in trigonometric form, or if I ask you to write it in the polar form, of course the formula is in the formula sheet, but this is what you need to do. So what you need to do, so first you calculate absolute value of z, so you need to answer what is absolute value of z. Second, you need to answer what is the argument of z. After you found these two numbers, then you have this formula, you write your complex number in the polar form. Yes? Of course, this is, I told you that usually in mathematics we have this tendency to make things simpler, not harder, but this is the first time we're making things harder. The reason is that something else that is more important becomes simpler. Okay, so for example, assume that as an example, I give you this complex number and I ask you to write it in the polar form. So what do? So let me write this. Write z equals to 3 minus I square root of 3 in its polar form. Okay? Okay, so but you have to start from here, but I have already done these two parts. You know that I have to calculate absolute value z, I have to calculate this. So you calculate absolute value of z, we already did that, the answer becomes this. You calculate argument of z, we already did that, the answer becomes 11 pi over 6 according to those calculations. So if I write this question in the exam, this part and that part are parts of the solution. And then after you found this one and that one as we did here, you plug them into this formula and then don't simplify, that's important. So z becomes absolute value of z, so this is the formula, theta is the argument. So this becomes 2 square root of 3 cosine of theta, and then plus I sine of theta. This is the answer. Don't simplify it more. Because if you simplify, you will get the same number back. That's not the point. So if you put this number in the calculator or use the table to plug these numbers in and simplify, it's not surprising. You go back to the original form. So don't simplify. The whole point is to change the standard form to a more complicated form. Okay? I will tell you why, but first learn to do this. For example, if I give you write this number I in the polar form. So how should I write that? So first of all, you need to know the absolute value of I. Absolute value of I is a square root of the real part plus the imaginary part. How can I imagine this number? The real part is 0. The imaginary part is 1. Yes, that's the meaning of I. So this becomes the real part squared plus the imaginary part squared. If you calculate that, it becomes, okay? Of course, for this one, there is a simpler way. If you imagine where I is, absolute value is the distance from the point corresponding to I to the origin, yes? So that's one, yeah, this one. But then where is theta? So if you need to locate theta, so you need to locate this point, 0. The real part is 0, the imaginary part is 1. So this is the vector for I, yes? And if this angle, you don't need to calculate anything at all. This angle is 90 degrees, or pi over 2. So this means that the argument of I, your complex number, is pi over 2. And when you have R absolute value of the number and the argument, you just simply write that your number I is equal to, the complex number is equal to the absolute value, which is 1, multiplied by the cosine of the angle argument, which is pi over 2, plus I sine pi over 2. Of course, I told you don't simplify, but in this case, you really don't need to keep 1 with you, yes? You can just take it out, because 1 times everything is just the same thing. But don't go further. Of course, if you go further, you will get the same I, because cosine of pi over 2 is 0, sine of pi over 2 is 1. If you go further, you go back to I again, which was not the point of this problem. So this is the polar form of this number. Yes? Okay, because of some trigonometric formulas, multiplying complex numbers in the polar form is not that hard that you might imagine. It becomes actually very simple. Let me just try to discover that. For example, if I give you 2 complex numbers in the polar form, let us see what happens. The derivation is a little bit lengthy, but immediately when you learn that, it becomes very simple. So let me say that I have a complex number, call it Z1. I managed to write it in its polar form. What do I mean by that? It means that I calculated its absolute value. It becomes this number. I calculated the argument. Let us assume that it becomes theta 1. And this is the polar form of my complex number. Yes? So I give you a complex number. You do some calculations. You find the absolute value. Call it R1. You calculate the argument, call it theta 1, and assume that you managed to write your complex number in the polar form. And then I give you another complex number, Z number 2. You do the same thing. You get probably another number for its absolute value. I call it R sub 2. And then you get another angle for the argument. So let me call it theta 2. Yes? And now my question is that, what happens if I multiply these 2 numbers? And what will be the polar form of the product? Okay, this is we have to do once. Yes? So let me see which one I don't need. Yeah, so you have some notes. Let me clean this one, but keep this. Might be we need that. Okay, so what we do, we start multiplying these 2. Okay, so let me make it visible here. Okay, I want to answer the question mark. So the question mark, which is Z1 times Z2, is equal to, instead of Z1, I put the polar form. Multiplied by, instead of Z2, I put the polar form. Yes? And then I start multiplying. Of course, R1 and R2 are just simple numbers, so I just multiply them. But then here it is a little bit lengthy, but we understand it's not hard. I have to take this and then multiply term by term here. So the first one multiplied by the first one gives me cosine theta 1, cosine theta 2. Okay? And let me immediately multiply this one by the last one. I times I becomes I squared, but I squared is minus 1. And this one multiplied by, oh, I made a mistake here. This is theta 1. This is theta 1. So I multiply this one by that one. I times I is I squared is minus 1. And then this one multiplied by that. Yes? There are two more terms. Which one? This one multiplied by the last one plus this one multiplied by the first one. So I just do that. So this one multiplied by the last one, I have I cosine theta 1 sine theta 2. And then this one multiplied by that one is I sine theta 1 cosine theta 2. Yes? But if you remember something from chapter 2, this is a famous formula. Cosine of one angle times cosine of the other angle minus the product of the sines. This is the subtraction formula for cosine. So the formula is cosine theta 1 minus theta 2. Oh, sorry, plus theta 2. This is the addition formula. Because for cosine, if you check the formulas, this sign is the other way around. It's the opposite sign. But what happens for this one? If I factor I out, so if I factor the I out, then this one is added to this one. This is the addition formula for sine, which becomes sine of theta 1 plus theta 2. And this is what actually simplifies things. So if I write the final formula for you, you realize what is going on. So if I ask you to multiply this I did it once. I don't want to do it all the time. But the pattern I discovered is very interesting. So it means that Z1 multiplied by Z2 is a very simple formula. You just multiply these R1 and R2 because they are real numbers. It's very simple. I just multiply them. And an interesting thing is that these numbers, theta 1 and theta 2, are added. So this is simply cosine of theta 1 plus theta 2. And then I have plus I sine theta 1 plus theta 2. Yes? So the pattern is very nice. If I give you two complex numbers in the polar form and I ask you to multiply them, you don't need to do it in this longer way. What you do, you just multiply R1 and R2. And for the reason that I try to demonstrate here, you just simply add the angles. Yes, it's as simple as that. And of course, I will not go through it, but this is also can be done if you divide these two numbers. A similar formula forms. To divide, you divide these numbers. But the interesting thing is that this time you subtract the angles. So this becomes cosine theta 1 minus theta 2, and then plus I sine theta 1 minus theta 2. This one I proved for you. This one I didn't, but that is similar. A little bit harder because you need to know how to divide complex numbers. You need to multiply by the conjugate of the denominator, if you remember. But that is what we see. So you see that even though it seems harder, still it looks harder, but at least you don't have any trouble with multiplying because you just simply multiply these numbers and then add the angles. Yes? Which was not that obvious from the beginning. that this pattern will emerge. Okay, now let us go back to say why the polar form is actually important. Let us use this formula, but instead of multiplying two different complex numbers, let me use the formula and multiply the complex number by itself. Let us see what happens. Okay, so let me give you a complex number like z, which is r cosine theta plus I sine theta, and I ask you to calculate z to power 2, calculate z to power 3. I don't know, calculate z to any power that you like. Of course, integer powers. I hope that you agree with me. This is extremely hard if I don't want to use polar form, because, for example, let me give you that number that I started with. Do you remember? It was this number. Okay? And I ask you to calculate z to power 100. So then it becomes extremely hard, yes, because what you need to do, you need to write 3 minus the square root of 3i to power 100. Okay, then you have to take this one, multiply it 100 times, which is a very, very formidable task. Or even if you want to use the binomial, Newton's binomial theorem, but still it contains 101 terms. Okay, so it's very actually hard. But using this trick, we can immediately answer the question. So now, if someone asks you what is the benefit, at least what is one benefit of writing a complex number in its polar form, the answer is simple. The answer is that using the polar form, I can raise complex numbers to high powers fairly simple. Yes, that's the answer to this. But how we can do that? Let me start with z2. If I ask you to calculate z squared, it means that you multiply z by itself. So what was the rule, do you remember? To multiply two complex numbers in the polar form, I am supposed to multiply these numbers, but I just need to add the angles. So what can I do? So I just multiply these numbers, yes? Because here there is no R1, there is no R2, both of them are the same number R, and then I have to add the angles. But what are the angles? Both of them are the same. Yes? But then R times R is R squared. But then theta plus theta, no one writes theta plus theta because people can simply write what? Cosine of 2 theta plus I sine of 2 theta. Yes? So, if I want to raise to power 2, I just raise this number. By the way, this number is no longer a complex number. R is the absolute value and it's always real. So I raise it to power 2. And that just simply multiply the angle by 2. Yes? So can you tell me what will happen if I raise it to power 3? So I have to take this one and multiply it by this one once more. So R multiplied by R squared becomes R cubed. And I have to add this angle to that angle. It becomes 3 theta, yes? Yes? So now if I ask you, if I continue this process and I reach to z to power n, what is the answer? The answer is r to the power of n cosine, what? N times theta plus I sine n times theta. Yes, so this is the reason. By the way, what I mean that if you are patient and to do it n times, the final answer is this. But we were able to do it without going through multiplication of it n times. We discovered the pattern, and now we were able to understand this formula. Is that clear? So now, for example, if I ask you to answer this question, so remember, sometimes they write it in polar form and ask you to raise it to high power. I don't think it's a hard problem because you have the formula in front of you. Sometimes they give you a complex number not in its polar form. They give you in a standard form and they ask you to raise it to fairly high powers. So then you need to remind yourself, okay, this is the place that I need to change my number to the polar form. So they don't ask you directly do it. You need to understand it yourself. Okay, so let us try to solve that problem to understand why this is useful now. I think you have written something on your notebook. So if you remember this number z, so the question is this. They give you this number, for example, and they ask you to calculate z to power 100. Let us see if we can do that. Okay, first let me, instead of 100, let me make it a little bit simpler. Let me increase the power a little bit so that the calculations become easier. So let me make it 600. And 600 in this case is simpler than 100. You will see why. And then I will come back to see if we can solve 100. Okay, so we want to raise this to power 600. Okay, so what we do, be careful. I want to skip some parts, but if this question is given in the exam, you have to do it. So the first thing you do, you tell to yourself that, okay, this is a complex number and this is extremely high power, this complex number. This means that you need to remind yourself about the complex form. So what do you do? I don't want to repeat that. So you have to calculate its absolute value, but we already did that. You need to calculate the argument. We already did that. Yes. And then you need to write your complex number in the polar form. We actually put this number here. We already did that. So then all of it will be the solution to one single problem, okay? Yes? So up to here, you have to calculate, so you have to solve that problem, this problem, and that problem in order to answer this question. And now the time is to raise this to power 600. But according to the formula, you need to raise this number to power 600. So is the formula in front of you? Yes, that is formula at the very bottom. And then, instead of raising it to power 600, which is extremely formidable task, we learned we can multiply it by the angle. Yes, so we can write cosine of 600 multiplied by 11 pi over 6. And then plus I times sine of 600 multiplied by 11 pi over 6. Okay? Here, there is nothing I can do. It's 2 to power 600 multiplied by 3 to power 300, yes? Because the square root of 3 to power 600 means 3 itself to power 300. You shouldn't expect to be able to calculate that. We just leave it like this. But then what happens here? 600 and 6 are simplified. It becomes 100 times. I multiply it here. It becomes 1100 pi. And then here, this becomes I sine, again, the same number, 1100 pi. Yes? First of all, it is done, because this is one single complex number without any powers for the imaginary part. But in this case, we can continue further. Can you tell me what is this angle? 11100, where is it? It's an even multiple of pi. So you know that if you have this unit circle, so if I start from here, go here, I have 1 pi. Then when I reach here, it's 2 pi. If I go one more, it is 3 pi. If I go one more, it's 4 pi. So you see that even multiples of pi are accumulating here, and odd multiples of pi are accumulating here. Yes? So this is an even multiple of pi. So definitely it will be some here. And when you want to calculate cosine, cosine means the x-coordinate. And the x-coordinate is what? Is just simply 1. And the sine is the y-coordinate. Y-coordinate of this point is 0. And this is extremely simple now, because now this is 1, this is 0, and then this is 0. So that's the answer. 2 to the power of 600 multiplied by 3 to the power of 300. So this is z to power 600. So I was able to answer it in a short amount of time. It's not that. But if I don't want to use this idea, multiplying them or using the Newton's binomial theorem, it will take ages, yes? That's the number. Yes, is that clear? So the philosophy for your lesson is that if someone asks you why, because you know that, of course I agree that this is harder. We are making this z looks harder, but the benefit is that if I am interested in that calculation, doing this calculation in this form is horrible, but doing it in this form is easy. So that's the reason that we bother about to write it in the complex form. But the reason that I change it to from 100 to 600, because it involves a little bit of trigonometry. That's why I even don't know if that's an angle that I can do. For example, if I ask you what is z to power 100, then what happens? Instead of raising it this number to power 600, it becomes this number to power 100. But then what I'm supposed to do, I am supposed to multiply my angle by 100 rather than 600. And then this is a little bit problematic, yes? Yes? Okay. But then, of course, if you have calculator available, then you can put these numbers in the calculator. But let us see, I don't know if we can calculate it on top of our head. So if I want to calculate, first of all, I need to have a good understanding of this angle. So this is a practice in trigonometry rather than complex numbers. Let us see how it goes. So for example, this one with 2 is 3, this one is 2 is 50. And then this one multiplied by that is what? 550 pi over 3. Okay, so I need to locate this angle, because whenever you want to find the angle on top of your head, if this is one of the famous angles, or I can relate it to one of the famous angles, then I can use the table or my memory to solve it. Otherwise, I have to use a calculator. There is no other way. So, but how can I do that? I need to try to locate this. So there are a lot of full circles in this angle, yes, because 2 pi is the full angle. And 550 divided by 3, I want to see how many full angles are included here so that I can locate it. So how should I do that? So for example, I divide 550 by 3. So approximately how much is that? So 180 times 3 becomes 400. So this is just, 3 plus 10. Is that right? Do you agree with me? 550 is 180 times 3 plus 10. Yes? Okay, so what can I do? I can write it like this. I can write 3 times 180 plus 10 times pi divided by 3. I would just want to simplify it as much as I can. Then I divide this number by 3, it becomes 180. Then I divide this number by 3. Of course, I need to multiply pi here as well. And then it becomes 10 pi over 3. Yes? Is that understandable? So I'm just trying to convince myself this angle can also be written in this form. But why this is easier? Because I don't need to care about 180 pi. Yes? I start from here. I go 180 pi. 180 pi is an even multiple of pi. So no matter how big this number is, I end up here. So this I can ignore. Yes, because I start going round and round and round. Whenever I cover one even multiple of pi, I will end up at the same point. So I can simply ignore that. So what matters is this angle. But this angle is also a little bit more than, so I can take it out. And here, this is also 2 pi plus 4 pi plus 3. Do you agree? Because that's also 10 pi over 3. So I can also ignore this 2 pi again, because that's also an even multiple of pi. So this means this is my angle. And how much is this angle? Is 4 times 16, which is 100. It is 240 degrees. So this means that I start from here, and then I end up here. So this is the angle 4 pi over 3. So if I ask you, show me the final point of this, by this analysis, you can go a lot of rounds, but you will end up with the same point. Then what matters is just this angle. So what is that angle? Is 240. So this means that this is equal to 240 degrees. So this means that this angle is 30 degrees. Yes? So then I don't know. If you haven't forgotten, in principle, using the table, you should be able to locate the x and y coordinates of that point. So what you do, for example, if you remember, I don't know, so you can go up, and then this angle becomes 60. You read the x and y coordinates of this point by looking at the angle 60 degrees. If you do that, if I remember it correctly, so the cosine is the x coordinate is 1/2, and this is the square root of 3 over 2. So now if I ask you what are the coordinates of that point, because of symmetry, you can write that. Yes? Okay, anyway, so that was the reason. You see 600 in this case was even simpler than 100. Yes, because you don't need to do this. Okay, anyway, so you end up with this point, read the coordinates, and then you put the numbers in. So I raise this to power 100, it becomes 2 to the power of 100 and 3 to the power of 50. And then if I ask you what is cosine of that angle ends up at this angle, and the cosine of this angle is the x coordinate, so it's -1/2. And the sine is the y coordinate. Yes, so that is your answer. Okay, so if you want, you can multiply things in. So finally, 1, 2, and this 2 are simplified. 2 to the power of 99 multiplied by 3 to the power of 50 with a negative sign. This one is also with a negative sign. This 2 to the power of 99 again. And then 3 to the power of 50, 3 to the power of 1/2. So this becomes 3 to the power of 50, 5 times I. It's a strange number, but that is it. Yes? So that's your complex number. By the way, let me try to see, because I hope that there is some features in GeoGebra, especially if these kinds of questions are given in that part that you are allowed to use the calculator. Might be it's a good idea to work with it as well. So let me see. Any questions here? So don't let this distract you. The hard part of it is not complex number. Might be because you have forgotten a little bit about trigonometry. So you see that up to here is exactly the way that I did before. But what makes it complicated is because I want to calculate this out of my head. Okay? If you have access to the calculator and you are doing that part of the exam that calculator is allowed, you don't even bother to think about it. You just put these numbers in the calculator. Yes? Okay, let us see if we can, because this lesson is finished here. Let me just try to see if GeoGebra is also capable of doing that for us. So let me see.